There are two sides to every story, and that is true with calculus too. We have been studying the one half called differential calculus. We have also been studying the other half called integral calculus, and today we're going to formalize our study of the indefinite integral. Hi, my name is Tom Atwater. In today's lesson, we will also learn to use the method of substitution to solve integrals. Let's get started with a definition. The family of all antiderivatives of a function f of x is the indefinite integral of f with respect to x, and it is denoted by the integral f of x dx. If capital F is any function such that f prime of x is equal to f of x, then the integral of f of x dx is equal to capital F of x plus c, where c is any arbitrary constant called the constant of integration. Although the definite integral and the indefinite integral have similar notation, they are quite distinct from each other in that the definite integral gives us a number, and the indefinite integral is a family of functions with a common derivative. Let's look at an example. Find the indefinite integral of the quantity t squared minus 1 over t squared dt. So to do this, what we need to do is antidifferentiate, which we've been learning all along. And we've been doing it actually since chapter 5. In fact, each derivative formula from chapter 5 has a corresponding integral formula that we will be taking a look at. So here we have that this will be equal to t cubed over 3 plus 1 over t plus that constant c. And so that's what that integral would be equal to. That's something that ought to look familiar to you since we've been doing these already during this course. All right, next what I'd like to do is look at some of the formulas that are the most useful ones, and you should familiarize yourself with these before moving on to the next section, in which when we look at function composition, and it'll be very necessary to have these formulas down. It's an anticipation of that section that in some of the formulas we choose to use the variable u rather than the variable x. So let's take a look. Properties of indefinite integrals. First of all, if we have a constant multiplied times f of x, that would be the same as simply multiplying the constant out in front by the integral of the f of x. And that's true for any constant k. Then we also have sum and difference formula, which says if you're taking the integral and adding together of either the sum of two functions or the difference between two functions, then you can take the individual integrals and sum those together or subtract those together. Okay, let's look at what are called the power formulas. The power formulas, the integral of u to the n du is equal to u raised to the n plus 1 divided by n plus 1 plus c. And that's true when n is not equal to negative 1. What about the integral of u to the negative 1 du? That's going to be equal to, of course, the integral of 1 over u du, and that's equal to the log of the natural log of the absolute value of u plus c. Let's look at some trig formulas now. We have 6 of them. Let's look at these 3. The integral of cosine u du is equal to sine u plus c. And the integral of sine u du is equal to negative cosine u plus c. And the integral of secant squared u du is equal to tan u plus c. the integral of cosecant squared u du is equal to negative cotan u plus c. The integral of secant u tan u du is equal to secant u plus c. And the integral of cosecant u times cotangent u du is equal to negative cosecant u plus c. Now let's turn our attention to the exponential formulas, which tells us that the integral of e to the u du is e to the u plus c. And the integral of a raised to the power of u du is a to the u divided by the log of a plus c. Finally, we will look at the logarithmic formulas, and that says that the integral of log u du is equal to u log u minus u plus c. And the integral of log base a of u du is equal to the integral of the natural log of u divided by the natural log of a times du, which, when evaluated, is u log u minus u divided by the log of a plus c. Now, I want to take a look at something to do with absolute values, and that is this, that since the indefinite integral does not specify a domain, you should always use the absolute value when finding the logarithm, or finding the integral of 1 over u du, which is the function log of u, because that function is only defined on the positive u intervals. And the function, while the function log of the absolute value of u is defined on both the positive and negative intervals in the domain of 1 over u. Let's explore Leibniz notation and antiderivatives. The limit of a Riemann sum of the form, the summation of f of x sub k times delta x, is the definite integral from a to b of f of x dx. The appearance of the differential dx makes sense in that integral. But in the indefinite integral, it may not seem apparent at first, but the dx is quite useful for dealing with the effects of the chain rule. And I think the best way for us to see this is to look at some examples of where we apply that particular formula. So let f of x equal x cubed plus 1 and u be equal to x squared. Find the antiderivatives in terms of x. So that's important. Find the antiderivatives in terms of x. A, we have f of x dx. For b, we have the integral f of u du. And for c, the integral f of u dx. So let's take a look at each one of these individually, remembering that in the original problem, we know that f of x is equal to x cubed plus 1, and that u is equal to x squared. So now we need to look at f of x dx, which would be equal to the integral of x cubed plus 1 dx. And that's going to be equal to, that's a typical antiderivative that we've seen a number of times where the function is already in terms of x, the differential is in terms of x. So we simply say that this is equal to x to the 4th over 4 plus x plus the constant c. All right, so now for f of u du, this would be equal to the integral of u cubed plus 1 du. Now initially we have both the function in terms of u and the differential in terms of u, that is du. So we can take our first step, which is that this is u to the 4th over 4 plus u plus c. However, we were told to find the antiderivative in terms of x. So we must make the substitution u is equal to x squared. So this would be x squared raised to the 4th over 4 plus x squared plus c. And therefore, we get a different answer than we did for part 1 of the integral of f of x dx versus the integral of f of u du. Here we needed it was very important to recognize the significance of the du here, and we had to make our substitution. And for our third one, f of u dx, well, that's going to be the integral of u cubed plus 1 dx. And now we've got a mixture here of the u, the function in terms of u, but the differential in terms of x. So we need to make a substitution immediately. And the substitution would yield that we're looking for the integral of x squared cubed plus 1, and my differential is dx. Now I need some space here, so let me erase a little bit, and I'll go up above where I've been working. So what I'm going to have now, bringing this over to here, this is x raised to the power of 6. So therefore, when I antidifferentiate it, I'm going to get x raised to the 7 over 7. Then plus x plus my constant c. So the importance of this particular series of 3 problems is recognizing that when you take the derivative of f of x, when you integrate the function f of x with respect to x, you get different answers when you have a different differential, or possibly a different differential than you have for the function. Now, substitution can be a great tool to change an unfamiliar integral into one that we can evaluate. It is important to change that differential as well, as we just saw. So let's take a look at evaluating an integral. Integral of secant 2x tan 2x dx, where u is equal to 2x. So if u is equal to 2x, then that means du dx, the derivative of u with respect to x, would be 2. And what that means is that du is 2 times dx. And what that now allows us to do is to make a substitution and change this particular integral into something that we're more familiar with. And so what this would be equal to is the integral of secant u, because that's 2x, tan of u, because that's 2x, and then the dx is 2, I'm sorry, it's not 2, it's the dx can be replaced with du, but we have to take care of the fact of this 2, which then tells me that I can put a 1/2 out in front of the integral, and that takes care of the 2 that was part of the dx. So now, this is recognizable. This is just going to be equal to the 1/2, and then the integral of secant u tan u is just secant u. Of course, we have to add on to our constant, and then I need to substitute back here. And when I substitute back, I know that u is 2x, so this is 1/2 secant 2x plus my constant. And so by doing that substitution of u is equal to 2x, we took something which was not necessarily familiar, turned it into a familiar form, which allowed us to find the integral by antidifferentiation. Okay, let's take a look at another example, because there are many techniques of using substitution. There's not just that particular one, so let's look at this. Evaluate the integral x dx over x squared plus 1. So the substitution we'll make is that u is equal to x squared plus 1. And that means that du is going to be equal to 2x dx. So our substitution then becomes that this integral up here is going to be equal to the integral of 1 over u du, but again, we have this 2 that's part of du that we take care of by putting a 1/2 out in front of the integral. And so now, this is going to be equal to 1/2 the natural log of the absolute value of u plus c. However, we have made a substitution, and we need to resubstitute back in, so it would be equal to 1/2 the natural log of the absolute value. Remember, we said earlier that we have to make sure that we're taking the natural log of a positive number, plus c. However, notice x squared plus 1 is always a positive number. So we can simplify this and give our answer as 1/2 the natural log of x squared plus 1 plus our c, and eliminate the need for the absolute value. All right, let's work another example so we can see yet another technique involved with substitution. Let's try making a u substitution and integrate from u of a to u of b. We have the integral from 0 to pi over 3 of tan x times secant squared x dx. And this one we're going to make a substitution of u equals tan of x. And therefore, du will equal secant squared x times dx. Also, what that means is we're changing from x in our function to u, so I'm also going to change our bounds. And the way we do that is we now say, okay, I want to evaluate u at 0. And u of 0 is tangent of 0, which is 0. Then I want to evaluate u of pi over 3. And that's going to be the tan of pi over 3, which is the square root of 3. So I now have my u substitution, u equals tan x, du equals secant squared x dx, and I have my new bounds, which are that we're going from 0 to the square root of 3. So this becomes the integral of u du evaluated from 0 to the square root of 3. And the u, of course, here is my tan x, and the du is the secant squared x dx. So therefore, we integrate u with respect to u, and that becomes u squared over 2. U squared over 2. And we're going to evaluate it from 0 to the square root of 3. So what this is equal to is the square root of 3 squared over 2 minus 0 squared over 2, which equals 3 halves. So clearly in this particular example, it was much easier to make a substitution and then evaluate the integral. Well, now it's time for you to try a problem. I would like you to make a u substitution and integrate from u of a to u of b the integral from negative pi over 4 to 0 of tan x secant squared x dx. Pause the video while you work on this problem, and when you are finished, restart the video to check your solution. Let's find out how you did on this problem. The u substitution that you should have used was the one that we used in the previous example. So u is equal to tan x, and du is equal to secant squared x dx. But you also needed to change the bounds, and therefore what you were looking for would be to evaluate u of negative pi over 4. And that means we want the tangent of negative pi over 4, which is negative 1. Then we also want u of 0, which is the tangent of 0, and the tangent of 0 is 0. So our integral becomes the integral from negative 1 to 0 of u du, which, as we saw earlier, is u squared over 2, and we evaluate from negative 1 to 0. And this time, we take 0 squared over 2 and subtract negative 1 squared over 2, which equals negative 1/2. All right, so that's your answer to that pause video. What a great section we had today. In this section, we explored the indefinite integral, Leibniz notation, antiderivatives, and be sure to work those exercises that your teacher assigns, and we'll see you next time.